Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on October 15, 2025, about 3 days ago. This paper proposes a simple way to feed functional MRI into large vision models. It shows that transforming 4D scans into 2D cortical flat maps and pre-training a spatiotemporal masked autoencoder yields strict power law scaling, and on HCP21 class cognitive state, decoding the best model reaches 98.8% with a frozen encoder. The paper is titled, Scaling Vision Transformers for Functional MRI with Flat Maps, and the implications for model training are quite significant. Beyond that, the model denoises naturally and transfers well across cohorts, reaching 84.6% on UK Biobank and exceeding chance by more than 8 times on NSD clip labels, while small models rival larger ones. Alright, the previous segment set the goals and results. Figure 1 shows the full pipeline. Surface-mapped functional MRI gets projected to a flattened cortical mesh, resampled as 2D images, and cut into square patches. The middle panels illustrate heavy masking, so only observed patches go into the encoder while the decoder predicts the missing ones. The right side depicts reconstruction trained with mean squared error, which encourages denoising and lets a standard vision transformer learn from video clips. So while Figure 1 sketched the pipeline, Figure 3 shows how reconstruction loss changes with data scale. The left graphs track train and test loss across steps for multiple dataset sizes, which reveals larger gaps for tiny datasets because the vision transformer overfits. The second panel plots test loss versus dataset size and follows a tight power law on HCP. The right side repeats this for NSD, where loss decreases but starts to flatten, suggesting limited diversity. Alright. Figure 3 highlighted strict power law behavior. Figure 2 shows side-by-side reconstructions for HCP and distribution and NSD out of distribution. Each panel arranges masked input, model prediction, and target for 3 frames, which makes the denoising obvious. The predictions look smoother than the noisy targets while still preserving structured cortical patterns. The left block corresponds to HCP. The right block corresponds to NSD, enabling a direct comparison. So Figure 2 showed denoising of structured cortical signals. Figure 4 reports downstream decoding and breaks results by dataset size, model size, and temporal patch size, and the trends differ. The left column shows a weak, non-monotonic gain with more frames, with small subsets lagging, and the biggest set best only on HCP state. The middle column shows that a 12 million parameter model matches the 89 million model, while the largest degrades. The right column shows smaller temporal patches consistently improve accuracy, because they provide finer time granularity. Well, Figure 4 reported downstream decoding trends. Figure 5 shows the pre-processing pipeline that converts raw scans into surface-mapped functional MRI suitable for flat maps. The left panel presents raw volume functional MRI in multiple views. The middle panel illustrates surface reconstruction and registration, which aligns each brain to a common template. The right panel depicts surface-mapped functional MRI on the cortical sheet, ready for projection to a regular image grid. Well, Figure 5 covered pre-processing. Table 1 lists 41 short captions used as global labels for the NSD clip benchmark, ranging from animals and vehicles to rooms and sports. These discrete labels come from nearest neighbor matching in clip text space, so the task reduces to predicting one category from brain activity. The breadth includes people, objects, scenes, and actions, which provides a compact yet diverse target set for evaluating cross-subject visual decoding. So 2 takeaways stand out. Mapping functional MRI to 2-dimensional flat maps lets standard vision transformers learn effectively, and masked autoencoder pre-training follows a strict power law while yielding strong decoding with even small models. The broader implication is a credible path toward foundation models for brain imaging, if training data grows more diverse. That is it for the AI Research Roundup. I am Alex. Thanks for listening.